Today we are going to discuss about the reactivity and the catalysis behavior of the organometallic complexes. Previously, we have already discussed about the synthesis part and the structure and the bonding nature of the metal and carbon in the organometallic complexes. So today mainly we're going to focus on the reactivity and the catalysis part. Okay. So mainly, basically, we're going to divide this chapter into two parts. The first part we're going to discuss about their reactions, that means the reactivity part, and in the later part of this chapter we're going to discuss about the catalytic nature of the different important organometallic complexes. Okay, and mainly we're going to discuss about the catalysis for converting the ethylene and carbon monoxide to useful products. Okay, so coming to the first part, so here we're going to mainly discuss about some important reactions, and usually the organometallic complexes are going to show many different types of reactions, and amongst them in this chapter we're going to discuss about the substitutions reaction, oxidative addition oxidative addition reaction. Third is reductive elimination, okay, deductive elimination, and fourth one is your insertion, fifth is your migration, sixth is your nucleophilic and electrophilic attack on coordinated ligands. Okay, so basically in this first first part of this chapter we're going to mainly discuss about the all types of reactions. Okay, so coming to the first one, which is substitutions. So let's turn the page. Wait. Okay, so coming to the first part, which is your the substitution reactions, and and actually early days, scientists did, they actually apply some external energy in the form of heat or some radiation like HNU. So what they did actually, let's suppose this is your LNM CO. This is an organometallic complex where n number of ligands are present. So L represent the ligands and M represent a metal, and the CO actually the carbonyl ligands. Okay, so when what they did, they first break this bond between the metal and carbonyl. So this bond, they break this bond by applying some energy in the form of heat or HNU. Okay, but sufficient amount of energy. Okay, the heat should be sufficient or the radiation should be sufficient. That means the frequency of the radiation must be sufficient such that they can break this bond. Okay, so once they applied this sufficient amount of energy, then what is going to happen, this bond is going to break and it is going to form LNM plus CO. So once this this product is going to form, but this is not a product actually, because you see here LNM, that means one ligand is missing, so that means one vacant site will be there. So that means a proper ligand can be joined with this with that vacant part or vacant side of that this complex. Okay, so that means this carbonyl ligand is substituted by some other part. Okay, understand, no? So as for example, LNM R3P LNM plus PR3. So this is your sometime actually carbonyl ligand can be also, this bond can be also we can break this bond by using some applying by some heat or radiation. Also we can break this bond even by applying some sufficient amount of heat or radiation. Okay, so this is your general reaction. So coming to some example, so let us discuss about some examples. So first example is your the nickel tetracarbonyl. Okay, tetracarbonyl. So what they did actually, when we first they by applying some energy let's suppose they first applying some energy, okay, energy, sufficient amount of energy in the form of heat or radiation, okay. They first get this one, okay. So since one vacant site is there, so what is going to happen if we add some ligand, then it will become NCO3L, okay. So again, if you again apply some energy, then what is going to happen? Again, that other CO1 CO we're going to remove from here, one CO we're going to remove from here, okay. Okay, so it will going to form this one. So again, if you add L, then it will going to form NCO2L2. So similarly, again, if you do, you apply some energy first step energy, second step L, then what will going to get? NiCO L3, and again first step energy, second step L, then you will get NiL4. So this is an example of synthesize or the reaction of metal carbonyl, and we can replace this CO, that means the carbonyl ligand, by some other ligand. So this is a substitution reaction, an example of substitution reactions. And actually, this is actually the substitution reactions is very easy. That means it will going to this is actually a very fast process, okay. This example actually, in case of nickel carbonate, the substitution process is very fast, because the bond between the nickel and carbonate is not so strong, so we can easily break this bond by using some appropriate amount of energy in the form of heat or radiations, and we can replace that carbonyl by using some appropriate ligand, okay. But in some other cases, like iron pentacarbonyl, it is not so easy to replace that by carbonyl, because we're going to discuss this, okay, why we cannot actually replace the carbonyl ligand from iron pentacarbonyl, okay. So this is an easy, actually this process is very fast process, okay. This process is your fast process. Well, fast, this reaction is actually fast, okay, because why the reason is the bond between the carbonyl and nickel is also strong, okay. But in the case of, let's discuss about some other examples, which is your here it is also written in that notes you see, but some will not lose carbon monoxide rapidly or carbonyl ligand rapidly. So as for example, iron pentacarbonyl, okay. So if you apply some heat and in the first step heat, if you apply first step heat or H nu and second step appropriate ligand, then what is going to happen? You can form CO4L, okay. So this is possible first, but again the second step also, one first is energy in the form of heat or heat or H nu, okay, and here second step ligand, then you can get CO3L2. But if you add more energy and ligand, then it will not going to give the further product, because the bond will going to become stronger. The reason behind that is actually the reason behind this this process is very interesting, okay. Here in the, if you go to the book, then you can able to notice the reason, or you can able to understand the reason that only actually two carbonyl ligands being displaced, okay. But it's actually in its time carbon when we replace that carbonyl ligand, then what by, let's suppose that L is your R3P, okay, triphenyl phosphine, okay. Not maybe triphenyl phosphine, or R maybe any group, okay. Trialkyl phosphine maybe also, okay. And let's suppose this is triphenyl phosphine, okay. Then we cannot proceed further, okay. For only up to this step is only possible. further addition of the energy, and the triphenyl phosphine will not going to give the FeCO to L3. It will not going to give that product. The reason is that when we remove one carbonyl from that ligand, then what is going to happen? That iron is become more electron negative, not electron negative. It become more electron rich. Okay, so electron rich. So iron will become more electron rich when we remove one carbonyl ligand. Okay, so what will going to happen? So what is the effect of this one actually? So when the iron become more electron rich, that means we already know that the iron in this bone, actually some pi bonding is occurring. This bone is strong because why? The pi bonding. But if the iron become more electron negative or electron rich, that means it can donate more electron to the antibonding para orbital of the carbonyl ligand. That means this bond will become more strong. Okay, understand? That means let us discuss in detail. Okay, let's suppose, again I'm going to explain it. Okay, so listen carefully. Okay. So when we remove some actually some ligands, that means the first ligand, that means carbonyl. Okay, let's suppose this is your iron pentacarbonyl, no? So when we apply some heat or some energy, okay, it may be some heat or it may be some H nu, that means radiation. Okay, then what will going to happen? FeCO4, it will going to form this one, no? So when this one will going to form, in this case the electron, this iron will become electron more, so this become electron rich. Okay, richer than this one. So what will going to happen? Yeah, since this become more electron rich, okay, that means the bond, how many carbonyls are there? 1 2 3 4. The remaining 4 carbonyl will be there, no? So that means here actually these bonds, we have already discussed the nature of this bond, carbonyl and metal bonds. These bonds actually, in this bond actually what will going to happen? The pi big bondings are there, no? It is already discussed now in previous classes. When metal is form bond with carbonyl, then the nature of this bond is what? It is actually not a single bond. Okay, actually one lone pair is donated from the carbon, which is your sigma bonding, and the T2G orbital of that metal will going to overlap with the anti-bonding pi molecular orbital to form what? Back bonding. Okay, so the when the iron become more electron rich, okay, then the previous then this one, then what is going to happen? This iron can donate more to the pi star anti-bonding molecular orbital. That means the back bonding will be, the extent of back bonding will be higher. That means this bond become more stronger. Okay, so that means when we remove one carbonyl, and it will going to give this one, no? So but to remove this carbonyl ligand from this complex is easier than to remove a carbonyl from this complex, because in this complex the iron and carbonyl bond is stronger because of the back bonding. This is the extent of back bonding. The extent of back bonding in this complex is higher than this complex. Hope you understand. Okay, that's why it is hard to remove carbonyl from this complex. And even this one is actually, even this one, in this case it will become more difficult to remove the carbonyl ligand from this complex. Okay, that's why it will not going to give the further products. Understand? So these are actually mainly the two examples of your substitution reaction solution. These are actually the scientists used this type of reaction That means they applied heat or radiation to substitute one carbonyl group by some triphenyl phosphine ligand. But there are some disadvantages, okay, of this reaction. So here actually some disadvantages are there. So what is the disadvantage actually? First disadvantage is that they will going to give side product. So side product means they will going to give some extra additional product which we actually don't want. Okay, so the efficiency of that reaction will be not good. That's why nowadays we actually did not actually we don't use this procedure, okay, to replace the carbonyl or to synthesis purpose. Okay, actually we use some different techniques or different method to prepare some new organometallic complexes from that carbonyl organometallic complex. Understand? Also, if you notice in the notes, okay, notes or the PDF, that you are able to find it. Here, it is written that the reason behind the the slow rate of that Fe CO5 this reaction. Okay, the slow rate of this reaction is, the first one is they said that the MCO bond strength, that means the strength of the M metal and carbonyl bond will going to increase, okay, because of that extent of your back bonding. And the second one is that steric requirement for phosphine limits the reactions actually, okay. So actually after this one, if you add energy, or if you apply energy and if you try to add the triphosphine, that means triphenyl phosphine, then because of that steric hindrance it will going to limit these reactions, okay. So this is also one reason behind that rate of that slow rate of that reaction, okay. Okay, so the drawback of these reactions are what? The drawback of this reaction is that the discussed reactions, actually it is written in the PDF, you see, the discussed reactions, that means the thermal and photolytic reactions give a mixture of products. That means it will going to give you some side products, okay. So it is not suitable for synthesis purpose. That's why we actually will going to replace this method by some new method, okay. So coming to the next page, okay. So in this some examples are given where they use some new technique, okay, uh, which leads which actually gives some specific product. That means we're going to get some specific product from this type of reaction. So first example is actually the one which in which they shows that, let's suppose this one, high temperature, they apply high temperature N or HNO, okay. So when they apply this one, then they will going to give actually many products, okay. The first one is normal WCO5 PR3. Second one actually cis product of tungsten CO2, sorry, 4 PR3 2, okay. And another one is your trans tungsten CO4 PR3 2. So actually if you look at this reaction, then this is actually the drawback of the previous this reactions actually enlighten the drawback of the previous or the earliest method, okay. So we cannot use this type of procedure. That means we cannot apply high temperature and the radiation to synthesis a specific product, okay. So what they did, they actually scientists actually use many different techniques, okay. So some techniques are given shown here. The first technique is they use tetrahydrofuran in presence of radiation, and they get tetrahydrofuran is complex plus carbonyl. Okay, so using this one, and this tetrahydrofuran can be this bond, the bond between the tetrahydrofuran and the tungsten is not so strong, so we can replace this tetrahydrofuran by you know by the tetraphenyl phosphine actually in room temperature. Even okay, even we can do this reaction in room temperature, and we can get the desired product C5, okay, PR3 plus TSF. So this can be uh, easily obtained by actually removing 3 TSF, because the boiling point is not so high, so we can remove this one, okay, by using some distillation process. Okay, so this is your first example, and in the if you go to the notes, then you can able to see some examples in which they use some different technique to prepare some products. Okay, so go to the uh, there are actually mainly two examples are given, and the last example is what the monosubstitute iron CO4 PF3. And then this process also they use some technique by which actually they can get only one product. Then so we can use these new types of methods by using which we can synthesize a specific products. Okay, so the main motive of this example is that previously we used a different technique, that means only we can use the high temperature or the radiations, and from that technique we can get many different products. Okay, so which is not good for us, because we actually want what we want only a specific product which is good for us. Okay, but if that reaction will going to produce more than one product, then it is not good for us, because we have to again separate them. Okay, to separate them we need to do another so we have to use some another method. Okay, so it will be going to consume some times, and also it will going to consume some you know uh, time, and also money also. Okay, so it will become costlier, no? So that means it is not efficient, or it was actually not an efficient reaction. Okay, so that's why we used some different new methods to prepare some specific products. Okay, so this is actually the main point. So now let us discuss about a very interesting point in the substitution reaction. Okay, which is actually the ligand cone angle. Okay, ligand cone angle, ligand cone angle. So actually this ligand cone angle is very important actually to designing a synthesis for organometallic complexes. Okay, so what is actually the ligand cone angles? So ligand cone angles actually come sometime what happened actually is let us suppose an organometallic complex, okay, metal, and let's suppose 6 ligands are there. Okay, 1 2 3 4 5 6. Okay, so let's suppose this complex follows the 18 electron rule. 18 electron rule. Okay, so if the ligands, the size of the ligand is very high, that means it is significantly high. That means then what will going to happen? There will be some interaction, because they will going to actually repel if the size of this ligand. Let's suppose the size of this ligand, and this ligand is high. Okay, then what will going to happen? They will going to repel each other. Okay, okay. So as a result, it will become unstable. Okay, though they follow the 18 electron rules, that means according to the 18 electron rules this is stable. Okay, but according to the steric effect it is not stable. That is the main point. Okay, so to understand the stability of an complex, actually we have to know about the 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 volume, or how many size is occupied by that ligand. We need to know about it. So a scientist known as actually Tolman, what he did, he actually in 1970 he introduced a new technique by using which we can measure the angle. Okay, and actually cone angle, that is the angle of this cone. Okay, angle of the cone which is made by that ligand to that metal. Okay, we can calculate that cone angle by using a very simple actually uh, instrument. Actually it is not a very simple instrument. Okay, it can even made by some piece of wood. Okay, so he gave, or he enlightened a new idea. Okay, and by using which we can calculate the cone angle. Okay, and depending upon that cone angle, or that the angle which is made by that ligand to that metal, uh, depending upon that cone angle, we can say whether the complex is stable or not, or we can design the synthesis actually, or design the synthesis of an organometallic complex, whether we can synthesize that complex easily or not. Okay, so he's actually the he gave the quantitative quantitative aspect of the measuring the steric hindrance. Okay, so his his instrument is shown. Okay, here. So this is his instrument. Okay, so by using which actually we can calculate the uh, cone angle. So what he did, he just he let's suppose this is your triphenyl phosphine. Okay, this is phosphorus. There are three phenyl groups are there. Okay, and he used a zero valent complex. Let's suppose L4. So L is here. L is what? Phosphine, phosphine or phosphite, phosphine or phosphite. So he used this one. So here, let's suppose this is your nickel. Okay, nickel, and this is a bone between uh, this ligand and nickel. Okay, so let's suppose this is explained. So what you have to calculate? We have to calculate the angle. Okay, so to calculate the angle, so we have to make the angle. We have to draw a straight line from the nickel, the center of the ligand, to the surface of the one benzene. Okay, one phenyl group. Okay, so at that angle, actually the distance from the center of the phosphorus to the metal is here. He found 228 picometer. Okay, so using this 228 picometer, okay, that means this distance, and we can have the by using some mathematics, we can calculate the angle which is made by that that ligand to that metal. Okay, so this is your cone angle actually, and if the cone angle is less than 160 degree, then it is actually then we can actually replace or we can actually replace some carbonyl ligand by that ligand. That means if the let's suppose this is your metal and this is the ligand, this is ligand, this is ligand, this is ligand, this is ligand. Okay, suppose. So let's suppose this ligand is your the phosphine. Okay, so if the phosphine ligand will going to make an angle of 160 degree or less than 160 degree to that metal, then this ligand, that means this phosphine, can replace carbonyl ligand and form a stable complex. So I am again going to explain this one. Okay, so let's suppose this is your metal. So if you don't understand, listen. Okay, so let's suppose this is your metal. There are some carbonyl ligands are present. Okay, 1 2 3 4 5 5 1 2 3 4 5. Let's suppose this is 6. Okay, carbonyl 6 carbonyl ligands are there. Okay, suppose. So we want to replace, let's suppose, 3 carbonyl ligand from this complex. Okay, by using actually by we want to replace 3 carbonyl ligand by 3 phosphine ligand. Okay, so let's suppose we replace. Okay, we just replace that. This is, let's suppose, carbonyl ligand carbon. Okay, so we can, the meaning of this, that this one is that we can replace that 3 ligand, that means the 3 carbonyl ligand from that complexes, if the newly formed, in the newly formed complex, in the newly formed complex, the ligand will going to form a cone angle of 1 less than 160 degree. If it is less than 160 degree, then that ligand, that means that ligand, it may be phosphine or it may be anything. Okay, that ligand can be replaced that uh, carbonyl ligand. Okay, so this is the concept. Understand? You can even understand this concept in some defined approach also. So let us consider the carbonyl ligand. Okay, metal carbonyl. Let's suppose this is your MO, molybdenal hexacarbonyl. Okay, so actually this cone angle is not so important in case of carbonyl, the organometallic complexes which has carbonyl ligand. Okay, the reason behind is that the carbonyl ligand is not so they are not sterically hindered. Okay, that means their size is small. Okay, the carbonyl ligand, the size of the carbonyl ligands are not so high, it is very small. Okay, so that means alone 18 electron rule 18 electron rule 18 electron rule can be, is actually is sufficient to to understand or to determine their stability to so organometallic carbonyl complex, in case of organometallic carbonyl complex, the 18 electron rule alone is sufficient to determine their stability. Okay, because their size is not so high. But if if the organometallic complex have many sterically hindered ligands, then 18 electron rule will not going to only the 18 electron rule not going to tell the stability of the that complex. Okay, so if you take an example of this one, metal molybdenal hexacarbonyl, then let us so this is your 18 electron rule. Okay, so here if you count the number of electrons for this complex, then you are going to get 18. Okay, the number of electrons will be 18. Okay, outermost orbitals. So let us suppose we want to replace 3 carbonyl ligand by 3 sterically hindered ligand. Okay, that means which in which the cone angle is more than 160 degree. Okay, so let us suppose we want to replace 3 carbonyl ligand from this complex by 3 ligand which has the cone angle more than 160 degree, then actually we cannot replace because of the because they are sterically hindered. Because if you design, let's suppose it is possible, okay, let's suppose it is possible to form this complex. Okay, that means 3 carbonyl ligand is replaced by the 3 ligand which is which have what the the cone angle more than 160. So this complex will be not stable, even though they will going to follow 18 electron rules. That means though this molecule or though this complex will going to have 18 electron rule, that means they will have 18 electrons in the outermost orbitals, but this molecule will not going to be stable because they have some huge ligand which will going to destabilize by repelling each other. Okay, that means the repulsion between the ligand, because of the repulsion of the sterically hindered ligands, the molecule is not going to stable. Okay, understand? So we can only replace two of them. Actually we can only form a compound like P. Let's suppose this is your ligand L. Okay, 2 ligand. So one, but we actually here you see we replace 3 carbonyl ligand by 2 ligand which have the cone angle more than 160 degree. Okay, so that means what, here it has 18 electrons now, but if you count the number of electrons, then it will be 18 electrons. Okay, so that means 3 to become stable, to actually to get a stable product, 3 carbonyl must be substituted by the 2 huge ligand. Okay, understand? So that means let's suppose this is your carbonyl. Okay, carbonyl. Okay, so if you try to replace only these 2 ligands by L, then it is not stable because they will go to repel. So what will we have to do? So we have to replace 3. Okay, we have to replace 3 by these 2 only, then they have some sufficient room. So here you see they don't have sufficient room, so they will going to repel with each other. Okay, but because we additionally we remove one more carbonyl. Okay, that means we remove 3 carbonyl ligand from this complex by only 2 ligand to get a stable product. But here in this case no doubt we'll get 18 electrons. Okay, if the 2 ligand will going to contribute 2 electrons each. Okay, then we'll going to 18 electrons for this complex. So that means according to the 18 electrons, this complex is stable. Okay, but here if you notice this one, it will not going to give you 18 electron or it will not going to follow the 18 electron rules, but it will going to give you 16 electrons, because you see one ligand is missing now, so 16, that means 2 electrons are missing, so 16 electrons. Okay, but this actually, but though this according to the 18 electron rule, this complex is stable according to 18 electron rule. Okay, but due to the steric hindrance, that means the steric repulsion between this 2 ligand, this is not stable. Okay, but this ligand is stable, though it is 16 electrons. Okay, understand? So but here one vacant site is there, one vacant site is there. Okay, because 16 electrons is present, so vacant site is there. So if the ligand is very small, if a new ligand, if you want to introduce a new ligand here, and if the ligand L1 is very small, then it is possible. That means this vacant coordinate site is available actually only for the smallest donor, very smallest donor. I think I hope you understand this concept of the cone angles, and they are actually contribution to the you know that designing the synthesis for organic complexes. Okay, so it is very important. So here in the next slide, actually, they gave they actually introduce one table here. Some important ligands are given, and also the some cone angles are given. Okay, so here L represents a ligand, so and theta represents a cone angle. So if you noticed here, then almost all have less than 160 degree. Okay, so that means they can follow the 18 electron rule. Okay, understand? So hope you understand up to this, and